My name is Maxime Jacquemin, and I will present to you what I've been working on since I've started my PhD in CA in France. I try. I'm supervised by Sylvie Puteaux from Polytechnique and by Frank Vedrin from CA. And my PhD is for now focused on floating point rounding error analysis, and more particularly on cheap way to obtain precise bound on absolute errors. To do so, we've decided to explore how to use relative error to improve absolute error bounds. And to enlighten why relative error may be useful, let me start with a simple example. Here we propagate informations with intervals on the variables. We propagate the value, the absolute error, and the relative error. The variable t is affected to the interval 1 to 100, and because it's an input, it's more simple. This variable does not have any error for now. After that, we have the variable x, which is affected to the interval 1 to 10 up to 4. And the floating point multiplication introduces an absolute and a relative error. The relative error is bounded by this value because of the standard, and it implies the absolute error we have here, which is caused by the biggest value of x. Okay, and finally, in the condition, when we consider only a naive propagation, we obtain those informations on R. It is affected to the interval 1, 2, but we have the same errors as x, which is a big over-approximation because the biggest absolute error of x are caused by the biggest value of x, and those values do not go through the condition. So we shouldn't have those absolute errors. But if we use the relative error here and the relation between the two, we are able to compute a new absolute error bound, which is far more better than the previous one. So our idea is to use the relative error, which is a natural error bound for rounding operation on floating point numbers, to improve the absolute error bounds thanks to a reduced product between the two. To present you this work, I will start with the floating point standard. We will try to be quick and simple on that. Then we will talk about how to model rounding errors, then how to abstract this model, and we will finish with some experimental evaluations. So, floating point numbers are approximations of the real numbers. Each floating point is represented by a triple composed of a sign, a significand, which is a finite positive real number, and an exponent, which is a signed integer. The floating point number represented by this triple is computed with this formula. And actually, we have two kinds of floating point numbers, the normalized and the subnormal. The details about them is not really important now, but the subnormal numbers are the closest to 0, and the normalized are all the others. But because the significand is finite, each time we try to represent a real number, we have to round it. And the standard defines rounding operators as functions that return the closest floating point number to a real with respect to a rounding mode. Several rounding modes are defined by the standard, but in this work, we are only focused on rounding to nearest with tie to even, but it's a technical detail. Okay, and finally, the standard defines one other concept we need, which is correctly rounded operations. It's operations that can be seen as the application of the exact operation following by the application of a rounding operation, which means that the result of the floating point operation is the closest floating point number to the result of the exact operation. The standard defines several operations as correctly rounded, like addition, subtraction, multiplication, or division, for example. Okay. Now let's talk about how to model rounding error, because if we want to estimate them, we need to understand them. We use this formula where Ex is the relative error we make when we round to a normalized number, and dx is the absolute error we make when we round to a subnormal number. And because we can't round to a subnormal and a normalized number at the same time, we can't have those two values different from 0 at the same time. We round to a normalized or to a subnormal number. Those two values are bounded by the format we use. We have the standard defines those bounds in simple precision and in double precision, for example. And finally, in this formula, we have the UFP, the unit in the first place. How we compute it is not really important, but it's the idea of the smallest floating point number with the same exponent as the value x. Which means that we can understand rounding operator as equivalently for all numbers with the same exponent. Okay, next we need to understand what errors are. So we use the standard definition of them, which means which are if we consider x tilde as an approximation of a value x, we can define the absolute error E of x as the difference between the two, and the relative error as this difference divided by x when x is different from 0. The relative error is not defined if x equals 0. Those definitions are standard. It came from physics, for example. Okay, now if we consider that our approximation is the application of the rounding operator to the value x, we obtain those two definitions. We call them elementary rounding errors because it's the error introduced by each rounding operation each time we try to do floating point operations. Okay, and finally, to be able to understand errors, we need to know how they propagate, through operations, and how operations add errors to them. So we use those two definitions, which looks like the previous one. We just consider that the approximation of the application of the real operation on real values is the application of the floating point operation on floating point values. These formulas are not really useful like that, but when we consider correctly rounded operations, we can expand them using the previous definition to obtain these formula, which are perfectly equivalent to the previous one in the concrete world, but will be useful to define precise semantics in the abstract. Speaking of which, for each variables of our program, we will propagate 4 informations, a range representing the real number, the real part of the real information of our variable, a range for the floating point range, and 2 ranges for the absolute and the relative error. Each of them is represented by an interval, which means that our values rely on the lattice of intervals. So we have a complete lattice and a component-wise join, which is sound only if we make the assumption that we have stable test, which means that we do not consider the case where floating point and real executions take different paths. Okay, so the main part of our work has been to redefine transfer functions to obtain precise evaluation, because thanks to the interval, we lost lots of correlation between variables. So we reorganized the expressions to reduce variable repetitions. For example, if we take how we compute the absolute error of a division. We do not actually need to understand all the math, but it's kind of funny, so I'll let them for you. Anyway, we obtain the final formula, which is quite good, but actually in this expression, we have this sub-expression, which is interesting because in the concrete world, it is equivalent to the relative error of y. And it's another way to use the relative error to improve absolute error bounds. Let's talk about that. We have 2 ways to use the relative error. The first one is to make a simple reduction after each operation. And the second one is to improve the semantics using the relative error in the expression of an absolute error, like for the division, for example. Okay, if I'm too quick, you can ask questions. Okay. Now, let's take some time to talk about an example. I want to compute the error bounds for this expression with t between 0 and 999. So our first step is to compute the error bounds for t plus 1. Here you have the expression we use for an addition, but because t and 1 do not have any errors, we can simplify them and obtain those two results. Here, for example, if we do not use this formula to compute the relative error, but try to compute it using the absolute error, we have a 500 times larger result. Sorry. Okay, and next, we try to compute the absolute error bounds for t divided by t plus 1 using the previous formula. We obtain those bounds which are far more precise than the bounds without the use of relative error in the expression. And finally, we compute the relative error bounds for t divided by t plus 1, which is not really interesting because we have real small values in this expression, which means we have really big relative errors. We can actually bound this relative error by the interval -1 to 1, but for the details about this point, I will send you to the paper. Okay, finally, let's just come back quickly on how we handle conditional statements. I show it quickly in the beginning, in the introduction, but here we can define more correctly, I guess. If we have a conditional expression which are called a gamma, the component of an abstract value x after the application of gamma, the interpretation of a conditional gamma, are obtained as follows. The values are computed by classical backward propagation and intervals. The relative error is left unchanged. We can't say anything about it. But actually, we can use the relative error to improve sometimes the absolute error using this formula. And this is why we obtain such a good result in the introduction example. Okay, we have implemented this reduced product in an abstract domain called numerals in the EVA plugin of Pharmacy, which should be available at the next release. And we have evaluated against state-of-the-art tools. The first one is Fluctuate, which is a known abstract interpreter specialized in floating point analysis. We decided to compare numerals to it because it used similar techniques, except that Fluctuate is based on a relational abstract domain. Next, we compared numerals to FPTR, which is a far more costly tool based on global optimization. It was interesting because FPTR is actually a more precise tool than Fluctuate, for example, and it gives us an upper bound of what we can target as precision. And finally, we compared to DAISY, which works in a similar way as FPTR, except that it has specific methods to propagate relative error directly. And this is the reason why we compare our tool to it. We make the comparisons on the FP benchmark, which is a benchmark specialized on floating points, and especially on floating point rounding error estimation. And we had some new benchmarks because we wanted to evaluate our capabilities on conditions. So we obtained those results for the absolute errors. I know the table is big. We will not go too far into the result, but here the important part is that the bold results are the best one. The italic results are the second best for the benchmark, And the columns are the following. The first one is another approximation obtained by random sampling. It's just to have an idea of what error we want to estimate. Next, we have numerals, following by two columns of fluctuate. The first one is used the interval abstract domain, and the second one uses the F-inform abstract domain. Then we have two columns for DAISY. We are not perfectly sure of the difference on the options we used, but we wanted to have a global overview of the possibility of the tool. Sorry. And finally, there is FPTR. The first thing we can see is that FPTR is far more precise on most of the benchmarks as everybody else. But FPTR is, as we can see on the second part of the table, costly. Next, we can see that numerals is the most precise tool on the three first benchmarks. It was expected because there is conditions on them. In particular, the first one is a loop that compute an approximation of a logarithm. And the two other benchmarks are conditions like in the introduction example. It shows that our techniques is really good to evaluate absolute errors on conditions. And the last point is that we are competitive against fluctuate even in affine mode. We obtain precise results, and on some of the benchmark we obtain more precise results as fluctuate. Another point is that numerals is really a low-cost analysis, which was our goal. Actually, fluctuate is faster, but we think it's caused by the cost of the platform we use, which is Pharmacy. Okay, and second table. It's the result of the relative errors bound. Here, fluctuate is absent because it does not propagate relative errors directly. We replace it with the posteriori column, which is an evaluation of the relative error using the absolute error bounds and the value bounds. We add a new mode for DAISY, which is, in our understanding, the most aggressive mode in relative error estimation. And what we can see is that FPTR still gives the most precise estimation, but again, it's a costly tool. But we are really competitive. We are the second most precise in most of the benchmarks. We are even able to obtain more precise results as a FPTR on some of them. And the other point is that we gave on a good part of the benchmarks more precise result as DAISY in its aggressive mode, which is really good with respect to the time we take to obtain those results. So, in conclusion, I've been too quick, I think. We developed and implemented an interval-based reduced product between absolute and relative errors, which gives us great enhancement on absolute error bounds for low cost. The next step is to use relational abstraction like xenotypes in fluctuate. And to go further, we think to explore tracking cancellations and local subdivisions. Tracking cancellation is when you subtract two floating point numbers which are really close, and the result you obtain can be only noises, which is bad for the rest of the program. And we think we can detect them because when we have cancellation, we have big relative errors. And the second point, local subdivisions, is that it's a standard technique to subdivide input of a program to improve the precision of the analysis. But when we want to analyze big programs, it is costly. But we think we can use the relative error to only make local subdivision on a subpart of the program and to obtain better bounds on the absolute error for this local subdivision. Thank you. If you have any question.
When you go backward for the conditions, do you iterate like in Granger local iteration?
No, I just do one iteration, just one time.
Would it be better if iterated?
We do not try it, but our goal was to obtain a low-cost analysis, so we consider that one iteration may be sufficient, maybe enough. But it could be interesting to try. There is a question here.
Which kind of relational domain you plan to use for future?
We think we will explore the notups.
That was my guess.
There is another question here.
The restriction to stable tests seems to have some potentially heavy consequences. So in the end, the results you obtain are of which form? So they are correct, assuming that the tests are stable, but can you do something better than this? Because
actually, to be able to obtain an interesting result with unstable test, we need to have relation between the variables, and intervals does not have any relation. So we think we can handle unstable test after using the notups in our domain. Any other question?
So it seems that here the baseline for your test is this FP Taylor tool, is that it?
Sorry?
The baseline you're heading out, the reference for your tool here is FP Taylor, which gives the
it gives the most precise estimation.
But in practice, what are the precisions you're after? I mean, is your tool doing a good enough job? And you didn't say much about that. Can you elaborate? Is the precision you get, is that enough for what you want to do, or do you have to go further?
On the benchmarks we have, we do not have much relations between variables, which simplifies the analysis. But actually, we obtain a similar result as fluctuate, which is used on industrial cases. So it's not that bad for, pretty good for a simple abstract domain like this one.
How do you explain the huge execution time of some competitors?
FP Taylor is interesting. It's costly because of its technique. It's used global optimization, which is quite a costly technique. For DAISY, I'm not really sure of why we have such a big execution time. It's quite enormous, I know. Maybe I don't tune it correctly. I'm not sure. I try to do my best to use it correctly, but okay. Thank you.